So let's write it rate of kinetic energy being generated. So the available propulsive power available is equal to m dot exit multiplied by u exit squared divided by 2 minus m dot f u f squared divided by 2 minus m of the free stream squared divided over 2. So given the fact that the u exit is much higher than my uf, which is my fuel, so I'm just going to ignore it. Or actually my inlet, I'm going to ignore it, and it'll say, well, P available is equal to m dot A multiplied by 1 plus the fuel air ratio and the difference in kinetic energy. So it's based on my fuel to air ratio. Well, my exit velocity is significantly higher than my inlet velocity, and this is P available, the power available we get by engine. Now these are parameters that, as I said, Boeing, Lockheed, Air Force, Navy, when they ask you for some of these, they're asking for these numbers, even the Army as well. Engines, a lot of airlines. Pull down a little bit. I'm sorry? Oh, lower? Yeah. So, how much energy we're putting into the engine? So that's what we call P in. And that's equal to the heat release. So reality is just Q. It's m dot multiplied by the fuel to air ratio that we're putting in multiplied by the heat of combustion. So the fuel to air ratio multiplied by the free stream mass flow multiplied by heat of combustion. We recognize this equation because it was a problem to right? But that's the P energy that I'm putting in, the P input. Actually, yeah, the lane terms is given as heat input. So we're doing a research project for the Air Force right now where we're characterizing different fuels for their afterburning engines. And one of the things that we're looking at is they're trying to characterize different fuels, JP5, JP8, and different camelina-based fuels, shell-based fuels for their engines. And one of the things that they're even asking us in the lab, say, well, match heat input when you're doing the experiments. And this is what a value, this is the maximum heat input you're going to get through the engine itself. So that's your heat input. Hopefully you get a chance to see that experiment. Okay, so another thing that we need is overall propulsive efficiency. So eta overall is equal to my propulsive work, WP, or the propulsive power, divided by my heat input, which is another critical parameter. So that's equal to what? This is my propulsive power, which we already said it's tau multiplied by my velocity versus my heat input, which we just listed up there. So tau multiplied by the velocity, velocity divided by my heat input.
P. No, let me just put P in.
Yeah, let me write this.
No.
Okay, So now you understand why we did the heat combustion and all that for this. Thermal efficiency. Well, thermal efficiency, eta thermal, is equal to the available power relative to my heat input. Again, that's why heat input is very critical. Well, that's equal to what we wrote earlier, is m dot A multiplied by 1 plus F u squared divided by 2 minus u squared over 2. The whole thing divided by the heat input fuel air ratio multiplied by the mass I'm putting through my engine multiplied by heat of combustion of the fuel that I'm actually using. So from there, I could simplify this equation and say, well, eta thermal is equal to 1 plus F multiplied by ut squared minus u squared divided by 2 fuel air ratio m dot A heat of combustion. Oh, sorry. And now you can see the type of fuel that you're using controls the thermal efficiency, the amount of mass you're putting in, the amount of fuel air ratio you're putting in, and the velocities you're actually generating.
Shouldn't that mass and bottom cancel?
Shouldn't that mass and bottom cancel? Did I miss that? So this will cancel out with this. Yes. Okay. So very good. Thank you. Now let's do propulsive efficiency. So we've done overall propulsion system efficiency. We've done thermal efficiency. Let's do propulsive efficiency, where we're not going to care about the heat input and characterize that. I might be able to say. Propulsive efficiency. Eta P is equal to, well, the propulsive power divided by the available power, which is tau u divided by m dot A multiplied by 1 plus F u x squared divided by squared divided by 2 divided by 2. And that's what we have for propulsive efficiency. Now overall, we already talked about it, that if we know the propulsive efficiency and we know the thermal efficiency, so we wrote the overall efficiency. But if I know my propulsive efficiency and my thermal efficiency, and you can see where I'm going with this, it's WP divided by PN. And this is WP available divided by PN, and this is WP divided by P available. So if I say overall is equal to my thermal efficiency multiplied by my propulsive efficiency. So from that, I will get the same exact equation. So if you compute this and you compute this, you already know this. Or if you compute this and you know this, you get this. And these are important parameters because some of the components we could actually figure out with this. Now, what do they really look like? If I plot some kind of routine diagram where the efficiency goes to 1 and this goes to 1. Got my box here. So my propulsive efficiency is always going to continue to increase because as I keep going up, my velocity is going to go up, my mass flow is based on the squares right here, it's going to continue to do this. And that's my beta propulsive efficiency. Now, thermal efficiency, as I keep actually going up in terms of my velocity or Mach number here, this is velocity or light Mach number. Oh, sorry. Or you can consider it light Mach number. So, this is your eta. So, as you're increasing your flight Mach number, you're actually doing less propulsive work out of the engine. And this is critical because this is where ramjets and scramjets become very, very efficient because, well, the name ramjet comes from ramming the air. You're ramming more air into, you're jamming in more air into the engine. Thermal efficiency, you already know that it's actually going to start to go down as you're going up in Mach. So this is why another reason we don't fly supersonic commercial jets, because, well, our tickets would be very expensive. Because thermal efficiency starts to go down as you're going up in velocity. So this is thermal efficiency. And overall efficiency is the multiplication of both, so my overall efficiency is going to look like this. Someone here is halfway relative to my velocity. And this is velocity relative to my exit velocity, how much I'm producing relative to the free stream. Now, ideally, in general, when you're using almost max power, you're right here of the engine. So, but when you're on low power, which is high altitude cruise conditions, that's where you're right here. So it depends where you're at in the flight regime that things could vary. So I think you had a question in the back and I had a question in front. Question?
Is the overall efficiency of this equation, the TH and the same one you put on the top of the overall system?
Yes. So I said that, but let's confirm this. This goes right there. Same. How's that? I needed to introduce those. Sorry. So that I can tell you that you can just do them all. Both. But yes, I mean it's the same equation, right? If I multiply this cancels out with this. Okay. Question in front?
Just what's that bottom curve, that the last one you drew on the graph?
Oh, thank you. Overall.
Okay.
This is the multiplication of both. Okay. I'm sorry? It depends, right? When you're taking off, it's a different condition than they actually, cruising up in altitude and you just, no turbulence, nothing, you don't have to worry about anything, then your velocity is actually very low relative to the free stream. So you can change and tailor the conditions accordingly. So yeah, this is a good question. So it really depends on your flight conditions, because these are dynamic engines. These are not just static. You're not designing it for one condition. This is why most are like, oh, why do we need MATLAB for this course? Well, because you can't just do what we did in high-speed aero and compute one condition. You have to use these equations and everything is changing. It is rocket science, right? So it becomes complicated as we start using the equations, but we'll step through it, and you'll be fine. I wanted to go over aircraft range. So let me start going over aircraft range, because that's a pretty critical one as well. Aircraft range. We want to always maximize the distance traveled by the aircraft. So want to maximize travel. Given the amount of mass of fuel. So, and this is a challenge because it goes against aerodynamics overall. You need very light vehicles, but you need to carry your fuel. This is why combustion is the most dominating approach for generating propulsion in general, because your energy per density for fuel that you're carrying is severely significant. It's very high. That's why you can't find any other resource to take it over. Anything you try to do becomes heavy weight relative to the fuel, and then you go back to the fuel. So think of it this way: you're loading a tractor trailer behind your car when you're using the same fuel that you're putting in the same gas that you have in your car. So it's the same principle. You don't want that excess weight. You want to reduce the weight as much as possible. But you're carrying a specific amount of fuel in terms of mass, and you're flying with that fuel to a specific range. Now that's critical because you want to determine what you need to get from here to California, and you don't need to run out of fuel before then, right? So, because then you're gonna, or New York from here, from Orlando, so the same thing. You wanna make sure that you have enough by the time you get there. And this is actually what's being used as well by pilots. And most likely your commercial corporations are probably telling them, don't fuel the full aircraft. They probably put like 1/3, 1/4 of what they can actually fill, because it's less weight and they can maximize their fuel efficiency by doing that, because then they're carrying less weight, they could run longer, and they have more profit margins. So that's tricks that I have to do throughout the whole process. So, and that's the same principle that we have to do this. And it comes down from, if we have a steady flight, thrust is really equal to drag. So thrust is equal to my drag force, and I can characterize my drag force by some lift divided by some characteristic, so this is lift, divided by some characteristic length over some characteristic L over D of the aircraft itself, meaning the length of the aircraft relative to its effectiveness area of core, and therefore that gives me my drag in a sense. So lift versus drag, so this is characteristic of the aircraft design. So if I know it, I could actually plug it in. However, I want to talk about one thing before we end the class. So I'm going to have to stop here. But let's pay attention to this, because I need to define it, because some of you asked me, I was like, oh, when are we going to have our next midterm? Because we have senior design, and we have projects, and we have things at the end of the semester, so let's strategically plan it right now. I wrote this, but in reality, I think we're going to have it right here. So you have the option between the 12 and the 14. Which big do you want?
14.
How much want the 12? How much want the 14? Some are not even listening.
I just don't care. Yeah, I don't care. Wait, what? 14? We have 14. 14? You guys can. Honestly, I just want to write this. Tap it out and draw it out. It's right there for you.
I mean, it's independent of the date, So the midterm is primarily covering ramjets and turbojets, both with and without afterburner. So that's what the midterm really covers. So
Whatever you like. You can do whatever you like.
and the 5th and the 7th, how is that for most? Okay. No, but I'm talking about senior design competition. Why do we have a week of senior design competition? Okay. All right. So, Sevens, I think some mentioned that they have a senior design competition.
Sorry, buddy.
What about the 19th?
You what? Dude, pushing it back somewhere?
No.
Yes. Yes. No. Yes. Yes. Dude, that's pretty close to finals.
I know, but I mean, what are we? I mean, we could do it at the end of the semester, the end of the month, 29th or the.
No.
But it doesn't matter. It's not cumulative. It depends on the topics we're covering, so it's independent, right? So it doesn't matter where the midterm falls, as long as it covers ramjets and turbofans. And then you're never going to be asked for it anymore, other than maybe the
And then when are you gonna have a
project.
final? Are you gonna have
Rockets.
just rockets?
Rockets and turbofans. 19th is fine. So in reality, second midterm covers ramjets, turbojets, afterburning turbojets, and the actually what end up is ramjet. I give you a project, so you don't. It's really turbofan, turbojets, afterburning and without afterburning. That's the second midterm.
Yeah. We have a project.
So that's the second midterm. The project 2 is ramjets. The final covers turbofans and rockets because we have 3 hours, so we have time there. And that's it, really. Turboprops is like turbofans, so that's most of the propulsion systems. So final is rockets, turbofans. Midterm 2 is really turbojets, afterburning and non-afterburning. Project 1 is ramjets, and now you actually covered all the different topics throughout. So you tell me how you want to design the dates. I'm fine with so material when it's fresh. So we're right here, 17. So if I say on the cover,
Okay, do the 14th.
ramjets within the next week.
There's gonna be a final and then we have a midterm. Or we also final to
Ideally,
midterm.
it's the 5th.
Or a midterm, a project, and a final.
It's good? All right, let's talk He said when it's fresh. But it doesn't matter.
Can we get hands up? We're not okay with that?
Okay, that's even worse.
What, the 5th? 5th? The 5th?
It doesn't matter. It doesn't matter. If anything, like he said, it's going to hurt you because you already covered the material right here. You're waiting right here. It doesn't matter. You're not going to see that material anymore in the final.
And we have a project towards the end. I'm not gonna do a project, a midterm, and a
Let's talk
final.
about it. But just